Sorry, one sec. Thank you very much. I'm going to pick up where I left off yesterday. And just remind you that this is work with several people. And so I want to recap how I want to break up topics between these two lectures. So what I covered yesterday was the idea that in this new class of endpoint materials, we start off with systems which have a different dispersion than we're used to, where, the TMDs and graphene, typically we have dispersion that starts where in a single monolayer, the low energy states are near the K point of the Brillouin zone. And so when you have the endpoint materials, we're presented with a new moiré reconstruction problem. So in order to set that up, I'll remind you what I talked about yesterday was stepping back and asking about the basic way to set up a moiré reconstruction problem. And in particular, I sort of advocated that for these sorts of problems, it's useful, while you can always do just moiré reconstruction just straight by thinking about a band structure and how it gets folded with the reciprocal lattice, I pointed out by a clever choice of coordinate system in the individual layers, sort of effectively a gauge choice, you can actually solve the problem by thinking about this effective momentum lattice. So that you can think of it as a momentum space hopping problem, and the distinction between bands which have dispersions at the gamma, K, and M points boils down to the kind of momentum space lattice that you get for this hopping problem. So in the case of the gamma point, you get a triangular lattice. In the K points that we're familiar with, that hopping problem was the sort of honeycomb lattice hopping problem. For each moiré block vector K, you have a honeycomb lattice problem that you solve. And finally, for the endpoint materials, we had this emergent Kagame lattice. And so what I used that to do was to set up, so today I want to tell you about sign-free Monte Carlo studies for one set of those materials. So this is when we'll introduce the roles of correlations. So again, this momentum space hopping problem, when you have a HOMO bilayer where the low energy electrons in each layer sit at the M point, you get this momentum space Kagame lattice. And I'll remind you what I said yesterday was that because the layers break inversion, the AA and AB stackings differ. And we had this picture where at each valley, the moiré potential only involved two of the three Kagame sublattices. And what I pointed out was that there's this emergent K-space non-symorphic symmetry that in certain circumstances can enforce quasi-1D behavior. And the example I gave was this AA stacked twisted tin diselenide. So this is one example of a material where you get this certain kind of quasi-1D dispersion. I'm going to sketch that. And I'm going to point out that for this material, the role of electron correlations can be understood in an essentially unbiased numerical way along two special axes in the phase diagram. And that will introduce two different ways of doing quantum Monte Carlo simulations. That will be what I'll talk about for the rest of this lecture. Okay? So just to say where that quasi-1D problem comes in, I'm thinking of this AA stacking of this TS and SE2 at this kind of 3.89 twist angle. And what I pointed out yesterday was that these bands, once you look at them, they're essentially trivial bands. They're flat, they're weakly dispersive, but they're also relatively trivial in this, topological sense, which means that there is no obstruction to constructing Wannier states for those bands, because you always choose some localized Wannier orbitals, use standard packages to do this. And so once you Wannierize, you can write down a tight binding model, and you can project interactions to those bands and write down real space tight binding models. There's a lot of work to do that. I'm just going to give you the results, but there's a sort of standard machinery. So what I'm going to present are results of what those tight binding models are. And so for the rest, from the purposes of this talk, you can essentially forget that these things came from moiré and just view it as a way of generating some interesting lattice model with some unusual symmetry structures. And the origin of those symmetry structures would seem very unnatural in many ways in a standard material. But the moiré problem makes those symmetry structures natural. So one can view the moiré at the level of this tight binding as, imposing some set of symmetries that we normally would not have been motivated to impose, or imposing certain types of dispersions that we would normally not think of as fine-tuned. They're not fine-tuned in the moiré setting, or they're less fine-tuned in the moiré setting. So that's a way to step back from moiré a little bit. And this can just be a talk on strong coupling physics, but in models that would seem strange if we didn't know they came from a moiré. So the specific model in this Wannierized thing has a single Wannier orbital in each valley, but on every site of this lattice, you get 3 valleys, and there are 2 spins. So you get 6 states per site, and those sites live on a triangular lattice. So I've drawn that here. Now, there's a little bit of a subtlety that I've drawn them slightly offset. So that's important because there is some local spatial structure. They're all very close to each other. They're much closer to each other than anything else. but the fact that the orbitals are not exactly on top of each other will affect the hierarchy of interaction. So that's something that's important to keep in mind. And a second point is that we'll see that these problems will have a particle hole symmetry which will map filling nu to filling 6 minus nu, and that will be important. Okay, and the thing that's special, and if you like, where the moiré comes in, is that one can think about this problem when I put in a kinetic energy for these sites. It's a hopping problem because it's tight binding, and that hopping is orbitally selective and quasi 1D. What that means is the following. So let's imagine I'm in the blue orbitals. The blue orbitals, this blue orbital can only hop to blue orbitals vertically above and vertically below it. It can't hop to the side at leading order. Similarly, the red orbital can hop along this principal direction of the triangular lattice, and the green orbitals can hop along that direction. So you have these color, this set of stripes that are in different colors, and they're rotated by 60 degrees, 120 degrees with respect to each other. And so the leading two-dimensional kinetic term that makes the system 2D is actually, so what could you write down that would take this problem? So this is some idealized limit. So you could ask, what pushes you off the idealized limit? So what are the second neighbor terms? So it turns out that if I had, you could imagine that maybe I could have something that went to the first neighbor if I want to go. So you could ask, well, if I want to go to the second neighbor term this way, it turns out that vanishes. So any 2D term in the red sublattice that you could say, what about a 2D red to red hopping along this direction? It turns out that's forbidden by one of these non-symmetric symmetries. So the leading second order term for the reds is to actually go a second neighbor over. So that's this. So for instance, the blues go that way, the reds go that way, and so on. So it's I'll sketch these out in more detail in a second. Yeah.
Particles are there. Yes.
Yeah, I'll show you that there. So interactions are where the physics of the orbitals get mixed. So there's an on-site Hubbard U, and there's a nearest neighbor V, and that nearest neighbor V is fully 2D, so it connects all possible nearest neighbors in the triangular lattice. And the orbital offset, so the orbitals are not exactly on top of each other, so they give you anisotropies in U and V. So for instance, the Coulomb repulsion on the red to red Coulomb repulsion will be bigger than the red to green or red to blue, just because the electrons and the green and blue see each other slightly offset. There's also an anisotropy in V, and if you think about it a little bit, you'll see that if I push things, if I think of this geometry and say, let's take this electrons all starting on top of each other and push them apart, then actually, given the orientation of orbitals, the red on this side gets closer to the blue and green on the other side. So this deformation of orbital offsets mean that the orbital anisotropies in U will always be opposite to that in V. Because if I weaken the red-green U term, I'll strengthen the red-green V term, just because moving it away from one moves it closer to the other side. But actually, it turns out that the anisotropy in V, while important for some very fine details, wouldn't be very important today. So I'm going to retain the anisotropy in the U. So another point to flag is that if I think about this alpha parameter, when alpha is 0, it's as though there was no interaction between the red and green. When alpha is 1, it means that red and green at the interaction level are identical. And there's a special feature of the alpha equals 1 point where the on-site terms are U6 symmetric and only broken by the hopping. So that's a special point because the atomic problem now has an enhanced symmetry. Even though the full problem, the fact that red can only hop to other red will break that symmetry down. It breaks it as a much weaker scale than the atomic limits. That's something to keep in mind. That set up clear? Maybe, I plan for being interrupted by questions because it's building on. So anything in this layout of these problems unclear? That's the model we're looking at. Yep.
Why do you think?
Oh, because spin and then valley, so it's SU6, and then there's charge as well, so then you can make it U6 roughly. Okay, so let's write down a Hamiltonian because I want to talk about that. So I've already said there's an orbitally selective hopping, so that means you go on nearest neighbors, and the hopping T eta has this thing where I've written T eta just to say it's the same strength, but on the green bonds it only hops green orbitals, and on the blue bonds, blue orbitals, and the red bonds, red orbitals this way. So that's this kinetic term. The interaction term I've already written down. It's just encoding the fact that the interaction between red and red is U, and the interaction between red and green is alpha times U. But there's also the V and H-perp terms. So let me write them down because they're going to be, so I'm going to spend a lot of time on these two leading terms, but it's always good to write down the leading perturbations away from your idealized point. So I'm going to keep those in mind. And so what are those? So I already said that I'm going to ignore, there's also a V term, which is what I'm drawing here is the V term will just be between nearest neighbors on the triangular lattice. So the V term hops the site's electrons this way. And so that has this feature. I'm going to ignore the anisotropies in the V. So I'm just going to say, well, that's a very small correction. So I'm going to say the V term democratically is just a second neighbor repulsion. Any electron here repels any electron here with the same strength. H-perp term is the leading term that takes the kinetic energy and takes it from having this special 1D filtered structure to making it something more physically two-dimensional that we might expect. And so it has, again, an orbital has a orbital dependent hopping. And so these are these dashed lines here. So notice that the green hops to another green, but it's a second neighbor hop here. So the naive thing which you'd have said that the green can hop to this one is actually forbidden by symmetry. And so that basically tells you that when you add this term, again, this is even this is an idealization because this relies on there being that non-symmorphic symmetry. Let's assume that it's there. So with that, even with that, you allowed the second neighbor term. But when you do that, if you think about each valley, so it's still all the valleys are decoupled from each other because at this point, I'm preserving valley U1 at the microscopic level. The interactions don't break that. So if you squint at this, you'll see that if I just take a set of wires and couple every wire to a second neighbor, that can peel apart to two rectangular lattices. So in some sense, when I put on this coupling, I still have 6 independent sublattices in the problem, 2 in green, 2 in red, 2 in blue. Okay, so that's the level of symmetry that you get. So I just want to explain what you get for each of these terms and the geometry that comes in. So you start off with wires in green, blue, and red, and there's no tunneling between the wires. Then I put on the tunneling. In each color, you're two-dimensional, but you have 2 different two-dimensional lattices in each color at that limit. And then there's another scale at which even this symmetry gets broken. So again, it's good to keep an idea of the hierarchy of scales. So in the idealized thing, without relaxation, you have this structure with the second neighbor. The ultra-idealized problem where I really say I throw away everything but first neighbor, it's the black terms here. Then the kind of more realistic thing, if you really believe the moiré problem and forget about things like relaxation, is this with this. The blue and red terms. And then if you really allow it to relax, then even this will be perturbed. So it sort of gives you the hierarchy of scales and the assumptions that are made at each level and writing down the two notes. Okay? So on top of this, we have interactions. I'm not going to say a lot about the interactions. There are 2 things that you could do to think about the interactions. You could work in real space, project the interactions, take the U and the V and any extended things that you get and extract those parameters by projecting a Coulomb interaction on the bands to the Wannier orbitals and extract some effective U and effective V. The other thing you could do is just take the momentum space states and do straight Hartree-Fock. And since we've used Hartree-Fock for lots of things, it's a good guide to the phase diagram. So I just want to sketch what you get by doing momentum and real space Hartree-Fock in the continuum model plus projected Coulomb interactions. Okay? And just stepping back from the tight binding limit is just working with the band that you get from doing the moiré problem. And I'm going to talk about integer fillings. So the qualitative picture, and the same color code works all the way here. At very weak coupling in Hartree-Fock, you get a gapless metallic state. And very strong coupling in a regime, what I'll call the flat band regime, then in that limit, you can essentially get a valley polarized ferromagnet. And that's sort of essentially when the kinetic energy doesn't matter. And in between, you get an antiferromagnet, which is what you get from a normal strong coupling intuition where the hopping actually has an effect, with and without valley polarization, depending on the details. So what you're showing is the same qualitative feature. What's different from nu equals 1, 2, and 3 is just the size of the supercell on which the numerics are done and the symmetry breaking and so on. But you can see that this is sort of a very coarse picture, but if you have a lattice model, you might want to think a little bit more about the strong coupling regime. So the polarized ferromagnet is sort of easy to understand. And gapless metal is easy to understand. The strong coupling states, you kind of want to have a picture of what happened. And in the strong coupling states, we have a language for doing that. We can think about taking the problem about the Mott limit and doing what you do in normal strong coupling perturbation theory for something like the Hubbard model. You just fix the filling per site and do virtual hoppings that generate super exchanges, and that will give you some effective Heisenberg model. That effective Heisenberg model will be a little bit strange because, there's also an orbital degree of freedom. So if you like, If anybody goes, if people have studied things like the transition metal compounds, there's all this work of Kugel-Komsky type models which have orbitally selective terms. There's in some sense a way of generating these kind of compass or Kugel-Komsky models where the there's an orbital selection. So how do I say, S dot S, depending on the valley you're in, whether you have a spin-spin interaction is valley dependent. So you have, like spins in one valley will interact with spins in the other valley, but only along certain directions. And so if the electron has a spin label, you have to worry about that sets where its Heisenberg couplings go. So that's what you can do at strong coupling. So what the thing to keep in mind is that if you had the limit where alpha was 1, so I'm going to work in that limit, I'm going to ignore the anisotropy in the U. At that limit, antiferromagnetic superexchange at order T squared over U will break U6 down to SU2 cross SU2 cross SU2. Because basically what that boils down to saying is I've frozen all charge fluctuations. I'm sitting on the site and I do perturbation theory. And in each color, I have an effective Heisenberg model, and that will have some anisotropic dispersion. So for instance, in one color, it'll be a set of Heisenberg chains pointing in this direction, another color the other direction. So when I think about how the problem works, I have to think about the combined effect of changing the valley and how the spin, when I change the valley, the direction of the spin interaction changes because some spins interact in some directions and some valleys interact in some directions and others interact in other directions. And it turns out that intuition means that we can play a game of drawing down bonds of certain colors, so at a given filling, and saying if there's an electron at a particular filling, it can couple to other electrons only if there's another neighbor at the site. If there's an electron of a certain color here, let's say at nu equals 1, on the next site, it can only couple to an electron by Heisenberg exchange if that site also had the same color electron. There's this sort of color degree of freedom that tells you how far an antiferromagnetic bond acts. That intuition means that it turns out you can exact results in the absence of this V term, which complicates matters, by mapping the energetics of the problem to thinking about the energetics of, you partition the system into spin chains of different lengths and just use what we know from the energetics of finite size spin chains. So let me see how that goes. For the simplest case of nu equals 1 electron per site. Yeah.
How can you spin the
No, because they'll be enforced by symmetry. So the colors will all be the same because, there's a symmetry of flipping between red, blue, and green. So they'll all be identical things. But it just means that a green spin can only couple to a green spin this way. There's no Heisenberg exchange to a green spin that way. But there is a Heisenberg exchange. Oh, I guess I said green goes this way, red goes that way, blue goes that way. So a blue spin, for instance, has no Heisenberg exchange with that spin, but has one with that spin. So if I put a blue over here, and I have another blue over here, they can interact by Heisenberg couplings. But if I put a blue over here and a blue over here, they don't interact. And so that gives you some understanding of how the couplings work. So let's see how that goes. I want to start with this lattice model where I put in all the valleys. And I put 1 electron per site. And when I put in an electron per site, I'm going to fix the valley of that electron. I'm going to just do that. And so I've got some coloring of the problem, right? So I've taken this thing and just put a coloring in. And I can ask, how does now adding on Heisenberg exchange? So for instance, this electron and this electron will interact, this one and this one, but these two don't because, I guess I said blue goes vertically. So these two interact, but these two do not, for instance. Yeah. So then I consider the strong coupling effective Hamiltonians, the usual Hubbard to Heisenberg antiferromagnet, but it's valley selective. So it has this thing where I've written SI eta ij because it checks whether the spin is in the right color for that bond. And so you get this valley selective coupling that tracks this valley anisotropy. So what that does for me is, for instance, let's imagine I put blues everywhere. Then I can compute the energy by just computing the energy. So in a finite, what I just do is calculate the energies per spin in an infinite Heisenberg chain, which I can do, for instance, by beta ansatz or numerical diagonalization. I can do that, right? So I just have to link connected sites when they're connected along the same color. Right? So for instance, if I broke this with a green, then I have to cut the chain, and that green one will have to talk to some other green spin over there. Or if I leave a green in there, it'll be an isolated spin. So I know how to compute it because every time I do the problem, what I do is just join up. There's a unique direction in which I can move. So once I do my coloring, I just join up everything by drawing green lines between green spins, stopping when they end. Blue lines between blue spins vertically, green lines between green spins in that direction. So then what I've done is color the system and draw it into partitioned it into a set of spin chains, and I can just compute the energy. Does that picture make sense for how I do that calculation? Yeah. But that is actually not too hard to do because I know the following. If I take a Heisenberg chain of length L and ask about the energy per spin, the minimum for Heisenberg antiferromagnetism turns out to be at L equals 2 when you form a singlet. It's sort of, you can give a monogamy of entanglement type of argument, because anything longer than that, you have to share your entanglement with a partner, whereas the dominant thing you can do is be perfectly antiferromagnetic with somebody else. So that means that I want to actually take the system and just color it by dimerizing. So I put a blue and I want to stop the blue, which means I need to go to another color. So that looks very much like I have a way of taking the system. It'll be a very degenerate ground state because there are many, many ways of coloring the system that way. It almost looks like the configurations of a dimer model on this lattice. A dimer model is just take sites and connect them. Every site must be matched to exactly one other site. Except there's a wrinkle. It's not if it was just a dimer model, much is known about the dimer model of the triangle lattice. One could go and look this up on the entropy, but in fact, Ming Rui and Hao Yu had to do a very tricky calculation here. The reason is that this is a special dimer model, which has a rule that says, sorry, I've written this wrong. It should be an always turn rule. So what it says, if I have a dimer, in a usual dimer model, I could have a blue dimer and then have another blue dimer over here. But if I did that, then by my coloring rules, I would have actually taken all 4 of them and put them into a length 4 chain. That would violate my rule that I should only have length 2 chains in the problem. So that means that when I have a dimer, the next dimer, I can't have a dimer here because the dimer model doesn't allow that, but I can't have another blue dimer directly on top of the other, which means my dimer configurations have to turn. So I have to go like this, and then the next one has to be a different color. So it's sort of this dimer model, which roughly says you have a color on the dimers, and so there's a second layer which says a blue dimer cannot be contiguous with another blue dimer. This doesn't allow it. Blue dimers only vertical bonds, and they can't be 2 successive blue dimers on a chain. So when you put that in, you get an extensive entropy that takes some work to calculate, but it's like 0.307 nkb, so finite entropy per spin. So it's a degenerate classical ground state of some solid. Quantum fluctuations will lift this degeneracy, but they dropped at this level. So it's some highly degenerate state. I think there's a question there? Yeah.
This states that
Yeah, that has much lower, it has lower energy. Because of this argument that the previous one would have partitioned the system, it would have put in the energy per spin of the infinite Heisenberg chain, which is, if you do by beta ansatz or whatever you like, you compute the energy per spin of a large Heisenberg chain, and you say, oh, but the energy per spin is higher when you have a long Heisenberg chain. When you have a short Heisenberg chain, the energy per spin is lower. So it's just this calculation here. Okay, so that gives us some idea of this strong coupling picture. And I won't go into it. You can do a similar thing at nu equals 2, a similar set of arguments, get 2 distinct valence bond solid states. And at nu equals 3 is very easy because when I do my coloring argument, it turns out the best thing you can do is just color everybody and then compute the energy exactly as a 3 sets of spin chains. So that's easy to do. And so we have this nice caricature of strong coupling states in this problem. Okay? Yep.
how do you put you put
That's at the very flat band limit. So I'm sort of throwing away, it's really when I'm in some limit where I've forgotten about the kinetic energy completely. This is like really the super exchange scale. I don't know if there's a clear way. It's somehow, this is clearly more honest, I would say, as a calculation than just doing Hartree-Fock blindly on the bands. There's some tight binding, careful calculation, but I don't know exactly how to match them. I don't have a great intuition. That's a good question. I think, yeah, they are kept there, I think. So there's some kinetic energy that's kept in. It's not a perfect flat band thing. So it's not just an orbital effect. You keep the kinetic energy when you did it. I have to go back and see when they did. We didn't spend a lot. I don't think we ever spent a lot of time on the Hartree. I should say this was really done by Hao Yu. I don't think he spent a lot of time on the Hartree-Fock because we were more excited about actually being able to do this kind of thing. So, yeah. Yeah.
Yeah.
Yeah. I think that was also with the V, which also complicates things. So this is also without the V, right? So you need a V for the ferromagnet typically because that sort of forces you to try and, you put everybody in there because the V plays a role. So I think that's also important. That's a good point. I kept the V there and then there's a competition. In the absence of a V, I think you don't get it typically. Yeah, thanks. Okay, so just as a summary, what we have is the sort of picture of a disordered classical dimer solid with, here I got it correctly, with the forced turn rule. two degenerate VBS with some particular root 3 by root 3 or 3 by 3 unit cells. And these are degenerate, so we have to think a little bit about how to choose between them. And this order, they're degenerate. And U equals 3, you get this sort of stacked chain state, which is just quantum disordered spins, right? So just Heisenberg chains. But, we have some lessons from, question?
Or if you can put it in, how maybe. Put it in, how you done it. That's fine. This thing
I think they're about as, I don't know, there's a famous quote from some geologist that one man's rigor is another's mortis, right? So I don't know what your version of rigor you want. I think at the level of problem, given the model that I put in, if I really were in the strong coupling limit and this Heisenberg picture was correct, and I could really map it to a Heisenberg model, there's some very large U at which I do believe this is correct, and it seems to be consistent with with our Monte Carlo and so on. But what kind of U you need to get there is sort of subtle. And I think one of the things you could ask is, this was done for the alpha equals 1, the isotropic point. And I actually think for the isotropic point, it turns out, thinking about the isotropic point tends to have a lot of special features because if you like, the hopping has to break the symmetry. So, it's a zero temperature statement. I don't know what the scale on which, the temperature scale on which this will get melted by thermal fluctuations is kind of interesting one. There's also an interesting question actually about the melting of this kind of solid, which I haven't talked about, which we kind of think of as a bit like a coiling problem, like a DNA uncoiling kind of problem, because you would say at finite temperature, it might make sense to have a longer chain because there's more entropy in a longer chain. So there's sort of an entropic effect that could actually think for a certain choice of parameters, we believe there's a regime where this thing could melt by actually lengthening the chain. So you could ask, what's the typical singlet correlation would kind of grow as you increase it because there's more entropy in the fluctuating chain. So there's interesting questions there. But at zero temperature, I think, if you're in strong coupling, these are, as rigorous as many other statements because, it's an exact mapping. But, again, it depends on throwing away the other terms in the Heisenberg model and so on. So then they could complicate things. So strictly speaking, if I gave you the Heisenberg antiferromagnet with this Valley symmetry, I think it's a rigorous statement. Whether that maps the Hubbard problem is a different question, right? And that's what I'll get to now. Okay? So, as often the case, we think that intermediate coupling is likely to be the interesting place. Like for TBG and other things, weak and strong couplings, we had an intuition, but to understand really what's going on in the experiment, often we want to have access to intermediate coupling. And usually our only hope for TBG, our example, was to work in intermediate coupling. We sort of did Hartree-Fock. We did this heroic work to set up the heavy fermion, the twisted heavy fermion model, the topological heavy fermion model. But even in the end there, one has to do a Hartree-Fock solver or DMFT solver or something like that. So you might want to ask if there's a way to do any kind of controlled analytical or numerical calculation away from weak or strong coupling. And, it's not a priori obvious that there are routes to doing that. So for the rest of this talk, I'm going to suggest that there are potential ways to do that in this problem. And maybe a way to think about this is that we can think of this problem as being closely connected, and this is sort of pictures that if you've studied these things before, up to a model of having, if you have strong interactions and you really keep the system 1D and forbid interwire tunneling, then one can think of this as a set of Luttinger liquids that are stacked in a particular way, because we know that strong interactions along a wire is sort of a Luttinger liquid-like picture. There's been work thinking about what happens if you have an array of Luttinger liquids that, these are 1D systems with strong interaction with no tunneling between them. What happens if I take an array of them, one like this, typically rectangular arrays of Luttinger liquids? We also have these sort of pictures. We know things about multi-orbital Hubbard models from DMFT. Also, there's work in cold atoms on what are called mixed-dimensional TJ models or mixed-dimensional Hubbard models. They were very useful for cold atoms because they give you some intuition. A mixed-dimensional TJ model is something where the spin interactions are two-dimensional, but the kinetic energy is purely 1D. A mixed-dimensional Hubbard model is like the problem we have. The interactions work in full two dimensions, the U's and the V's, but the kinetic energy has some special structure that it only goes in one direction. Okay. And also to motivate why we might want to work at strong coupling, it's useful to ask oneself, how strong is strong coupling in a model with U and V? And the reason for that is that U and V tend to counteract each other. And this is sort of, there's a nice old paper by Sasha Lichtenstein and others that points out that, if you have an extended Hubbard model with a U and a V, one can ask by asking about like a goodness of fit of some density matrices or something like that, whether you can approximate the ground state of this problem You could ask, suppose I didn't want to treat a Hubbard model with with some second neighbor V. There may be various reasons why you don't want to do that. You could ask, is there a way to come up with an effective U star for the Hubbard model that is an on-site U star that effectively captures the effects of V? And so one way to do that is there's a way to think about it by doing some variational calculations. So these are these are expectation values taken in a ground state with this effective coupling U star and no V. And this V is what you want to kind of emulate. And so there's sort of a variational argument that leads to this kind of proxy. And what you find if you run it here is that the effective U star that you get, you can think of the physics of the extended Hubbard model with U and V as being roughly connected to the physics of an ordinary Hubbard model with U suppressed by U to U minus V. That sort of suggests that even if you start at strong coupling, because the V is there, the problem will actually be at much more sort of closer to intermediate coupling because the V is counteracting the effects of the U. So just ramping up U is not going to be that useful. Yeah. And so just to think of what we did here was just plot this axis is U over T, this axis is V over T, and this is something like a gate distance for a double gate screen moiré sample. And we asked, where, so what we're sort of saying is that, for different gate distances, you can see there's a busy plot, but it's just showing you where all the different kind of realizations will be for different twists and different kind of various parameter choices. And what you see, I think, and this is for different twist angles. So I think what you see is ignore the U equals 3V. That's some place where Quantum Monte Carlo, or a certain type of Quantum Monte Carlo stops working. I'll come back to that. But if you look at this broad phase diagram, you say, okay, so when does strong coupling seem to work? And if you go through and kind of match our results, what we seem to find that strong coupling seems to work only down here. So most systems are kind of intermediate coupling where these, somebody asked whether those results were rigorous. Well, the results I presented on the previous page don't seem to work very well except away from this U over T of order 12 and no V point. Once you start adding these other terms, it sort of pushes you away from strong coupling pretty quickly. Yeah.
What is like because it's nothing.
Oh, I'm not talking about anything about a phase being realized, right? There's not a phase diagram. I'm just shading this as saying where sign-free QMC works. And I'm just doing a sign-free quantum Monte. What?
What is it?
Oh, the yellow color is where there's no sign problem. It turns out that for this problem with the U and the V, I'll show you in a second. And this is actually for a particular sign. So I'll show you what I mean by the yellow in a second, okay? That's why I said ignore the yellow for the moment. Yeah.
Situation where there's like
yeah. Absolutely. I'm just saying as a proxy for what we think of as strong coupling. I'm not using this rigorously. I'm not going to simulate a model with only U and V. I'm going to put it, I can do everything because I've got sign-free QMC, so I don't care. I'm just saying if I want to believe a strong coupling result, there's a useful proxy for asking, should I trust the strong coupling result? And I think this is all I would say. I'm not saying you should throw away the V, but I'm just saying that naively you might say, oh, U is huge, but if V is also big, the effective U, that's all I'm saying from that. Yeah, that's the only point. But thanks for the question. Okay, so how can I do control calculations in intermediate coupling? So I'm going to put up a phase diagram and show you where I have some control. So on the x-axis, I have the filling, so 1 to 6. And on the y-axis, I'm putting on T-perp. I'm going to imagine I put on this T-perp, this second neighbor, same intra-valley hopping term. And so if you look at this, I'm going to say the following, which is I have a special feature that there's particle hole symmetry about half filling, partly because of various things that this model is bipartite and so on. So there is a particle hole symmetry that you can work out. Surprisingly, it's a model on the triangular lattice. The triangular lattice is not bipartite, but with all these orbital structures and the nature of the hopping, essentially it becomes a bipartite problem and you have you're sign free. And this is true for any value of the T-perp. So that means that I can do auxiliary field quantum Monte Carlo, where the computation of fermion determinants is sign-free because I have an anti-unitary particle hole symmetry. I'll explain what that means. It's just to kind of flag, to presage what is going to come. What's also very surprising is suppose I agree to take this idealized limit where I turn T-perp to 0. I have this model where the kinetic energy is purely one-dimensional. If a kinetic energy is purely one-dimensional, for a one-dimensional problem, the fact that I have fermions is never a problem because I can Jordan-Wigner my fermions. The reason this doesn't work in 2D is because two fermions can talk to each other and say, hey, what is your Jordan-Wigner string and where's your Jordan-Wigner string? You have to compare them and then life gets very hard. But if the fermionic kinetic energy never can take a fermion and hop a fermion from one side to the other, they'd have no way of knowing what each other's Fermi statistics are. So along this axis, the problem is also sign-free. And in fact, it's sign-free within some sense, what I think of in some ways the gold standard for lattice model Quantum Monte Carlo. We can apply the stochastic series expansion. And so essentially that means that we can go to very, very high order, high precision and do very large systems. So along these two axes, it's not the full phase diagram. We really care about something out here. But if you like, we can start getting somewhere by seeing maybe if we're close to one of these points, we can get intuition by doing this analysis and then perturbing. So that's what I'm going to try and do. And I'm going to just tell you some first results of Quantum Monte Carlo along these axes. So I'm going to call this doping the sliding point, and this one is telling me about going two-dimensional. So in some sense, this keeps two pieces of physics alive. On this axis, I get a good intuition for things like something an experimentalist might want to do, which is, tune the doping and ask about how you go between correlated insulators to metallic states and so on. And along this axis, I have some intuition of what happens at some special filling where I can worry about the fact that the system is not really quasi-1D, it has these 2D couplings. So I can address each of these along, get two complementary pictures. At a fixed filling, I can see what happens when you go 2D, and in this really quasi-1D limit, I can dope the entire range of fillings. That's sort of a nice feature. Okay, let me do them in turn. So I won't say much about methods because I think if you want to do justice to a Quantum Monte Carlo method, you need a whole series of lectures on their own. But let me just say what it is. The stochastic series expansion actually goes back to very, very old work in the 1960s and 70s by Hanscom. And it has, dates back to people thinking about how to do high temperature series expansions, which is a precision way to do it. What this does is basically stochastically sample the high temperature series expansion for the partition function. So you have e to the minus beta h, and what stochastic series expansion does is just say, let's just expand this in a clever way in a particular choice of basis. So what does this mean? I'll expand it out. So what it says is that I can rearrange the computation of the partition function. This is just some work where you say, I can think of this as computing a set of operator strings. And if I have a simple enough states, if I work in the Fock basis, and I think about local Hamiltonian terms, I can sort of think about, anything term in a series expansion, the Hamiltonian is just a sum of terms that act on different bonds. So a term in the series expansion is just a product of terms on bonds. So, of course, I want to calculate an expectation value like this, but the way I can compute that is to say, let's say I had some term here. If I choose the basis correctly, this H will act on this state and not split it into a superposition of states. It'll just take that state and take it to another state. And then I can take that other state and some other H will take that and go somewhere else and take that and go somewhere else. So that now looks like I've got kind of a loop where I have a time direction, this alpha L plus 1, and I've got some length of loops. And what I'm trying to do now is just sample these things. And I can just think about that as a stat mech problem that I then sample. And for this to work, you need there to be no branching because otherwise this won't be a string. It'll start off with a state, then it'll split into two states and then I'm lost. So this can't branch. And I need this object to be positive semi-definite. So I need these terms to be have a particular sign. And if those things are satisfied, I can actually sample this because it's just some complicated probability distribution over strings. And it turns out there are sort of special updates that are similar to the Whirl-line updates for bosons or things like that, which are called worm updates or directed loop updates. So for instance, what you do operationally, so what you operationally do is as you go down to low temperatures, you'll have to worry about strings of longer and longer length. But there's some knowledge of, you say you actually truncate at many times what the average thing is, and there's some good understanding. You have to do some benchmarking. There's some good understanding of tails. So it's just sensible to just pad it with 0 strings and just put in some, and say there's a maximum string length cutoff and then do that. And that will have to adjust as you go.
What to call it?
Which one? Yeah, this is, I think it's in the, I think this is actually an exact thing because you have a sum over all lengths. This is sum over all strings. And if you do that, this one is fixed. Yeah, sorry, this should be an approximate. Sorry, yeah, you're right. I think the corrections are exponentially small if you're careful. So I think it's almost as good as an equality. But yeah, you're right that it's a controlled thing, but you have to actually fix L dynamically. Good. Yeah, thanks. So there's something, for instance, just to say that it can be done for the 1D Hubbard model, I know exactly how to write down these operators. Yep.
How do you pick alpha then? And is it just some basis?
That's an important thing. You have to pick a special basis. It's always some simple computational basis, right? So for spins, for the spin chains, it would just be the Z basis or something like that. It turns out that if you choose the wrong basis, you could go very badly wrong. And we think that previous work actually chose a basis that was adapted to the U equals infinity limit. And we think that if we tried that basis first, and it just doesn't work when you move away from u equals infinity. So you can get into trouble if you choose the wrong basis.
So, wrong math or like
I think it just things didn't converge. So it took us a year to do this. So there's lots of benchmarking in the background. So this was started in September 2024, November 2024. So it's been a long run. There's no paper yet because it took so much work. So I'll tell you how this works. So for instance, when T-perp is 0, what I said is the fermion whirl lines never cross. So each chain is sign-free for a stochastic series expansion. And so what you can do, and we're not primarily numerical physicists, so I'm sure somebody with real skill can do much better, although Dimitri is pretty amazing at this. You can do up to 12 by 12 systems, 2D quantum problem. You need to have a good basis choice. That's exactly what you said. You need a special basis choice that, we have a particular one that's nice, and I have to look back and tell you what it is. It's not unnatural. And you need clever updates, and the clever updates is the trick. So it turns out for this particular problem, one way you can think about it is in Monte Carlo, you want to sample over all configurations. So you need some way for the electron to jump from one valley to the next. The kinetic energy can't do that. There are no terms that mix valleys. So we had to do some updates that flip the valleys. But any naive update that flips valleys turns out to be very, very bad at equilibrating. It was just horrendous. So there was a very clever trick that Werner Kraut, unsurprisingly, was a master of Monte Carlo, and Dimitri came up with, which is that usually when you do these worm algorithm updates, what you do is all the rejection steps. You try to do a step, and in Monte Carlo, the traditional Metropolis algorithm is saying, propose a move, reject the move based on the Metropolis, the Hastings Metropolis weights. Now, the problem is that when you do a directed loop update, all that goes into preparing the state itself. So you sort of, you ask, can I do this or not? And then when you build a loop, you always flip it. And it turns out that was very restrictive. So what these valley flip updates do is don't ask the question until you constructed the full loop. And so some of the time you build a loop that shouldn't be flipped, but you do Metropolis on a non-local loop. And that's kind of a weird trick, but that actually turns out to equilibrate the problem and things like that. So it's sort of an important thing for people who are doing Monte Carlo. So what can you do with this? There are two things that you can compute naturally. We have access to the Green's functions, but that's why it took an extra year. That's much, much harder. But the simple things you can do are two thermodynamic observables, which is what I'll present for you today. One of them is the inverse compressibility, which is just d mu d nu. And what it does is measure the energy cost for adding or removing a charge. And so this is a nice thing that we want to look at in an insulator. It's directly measured effectively in experiments. And we expect this to peak at an insulator and to be small in metallic states because metals are compressible, so their inverse compressibility will be small. Insulators are incompressible, so their inverse compressibility will be very large. Another quantity you can compute is what I'd call the charge stiffness. This was, a very famous paper by Walter Kohn characterizing the insulating state. And what it does is look at the second derivative of the ground state energy with respect to a flux. Operationally, that's what it measures. And what it does is measure the flux response of a sample in a torus with a flux threaded through a loop. And why does that do that? If I have a flux through a loop, by Lenz's law, you'll generate electric fields in the loop if I try and dial up the flux. And that means that there'll be currents moving in there. So this response function will be large in a metal and will vanish in an insulator because it sort of effectively thinks about the conductivity of the system in some sense. It's not strictly a conductivity because a conductivity can't possibly be a thermodynamic observable, but it's a proxy for being in a metal or an insulator. And each of these has a good estimator in stochastic series expansion. This one is pretty easy. It's just, as you might imagine, is just linked to number fluctuations, essentially by some fluctuation dissipation-like theorem. This is a little bit trickier. To think about the flux response, maybe a way to motivate it is to respond to a flux, somehow charges need to go all the way around the loop. And so in stochastics, in Monte Carlo algorithms that work with whirl lines, you have access to trajectories of particles that go physically entirely around the system. So what you then do is just count the number of configurations in Monte Carlo that actually wind around. So effectively, you calculate a winding number of these trajectories. And this very complicated form over here, I was convinced it could be made less complicated, but Dimitri now has told me there's no way you can possibly do it. I tried and very hard. What it just does is that if you have something that's a triangular lattice, there are many ways that you can wind around the loop. And so it just captures all of those different ways. But essentially, in each way, it calculates the number of things that move up versus the number of things that move down and takes a net difference. And that gives you a measure of the winding number. So both of these are things that you can just sample, like while you're doing your Monte Carlo. They're things that you naturally keep track of in your statistics, so you can get them very easily. So if you put this on a computer for long enough and, create a clearing in the Amazon with the carbon that you burn, then you can come up with some nice plots. And so that's what I'll show you. So these are now results from these numerical studies, right? So I'm just picking some representative value of U and V. And there's a neat feature that you dial the system between what I'd call weak coupling and strong coupling. And what you see is that, and so the way we pick these rather peculiar numbers is sort of taking a particular twist angle in a sample and dialing the gate screening distance. So there's some particular ratio that just comes from the geometry of the problem. It's not that we pick them out of thin air. But at weak coupling, what you see is, because it's particle hole symmetric, I'm only going to show you what happens between 0 and 3, and from 3 to 6 will be captured on the other side, right? So from here on, it's just a reflection of this. What you see, and I'm going from hot to cold, so beta is coolness, so this is colder up here. As you lower the temperature, you start seeing peaks, but notice that at weak coupling, you see the strongest insulators near half filling, whereas at strong coupling, you see the strongest insulators near nu equals 1. So it's sort of the trend of the strength, the insulating states, the hierarchy of insulators is reversed between weak and strong coupling. And there's a nice way to think about this, both from the weak coupling picture, we can think in terms of bosonization, and so I'll sketch how that goes. In the strong coupling picture, we can think in terms of something like a fluctuation calculation about a strong coupling state. So just all you should take away from this is insulator at 1, much weaker than 2, much weaker than 3. Trend reversed, insulator at 1, much stronger than 2, much stronger than 3. So I think everybody can see that from here, right? Just very obvious, it just jumps out at you. So a way to see that at weak coupling, and I will just jump through this if, it's one of these things. So what bosonization does is take a one-dimensional problem and essentially map all the physics of fermions into something that looks like a quantum 1 plus 1D XY model. And that XY model has some phase and dual phase degrees of freedom. And so if I take this problem, on each valley spin, I have a right or left moving electron, and I can rewrite it in terms of phase variables theta and phi. And then there's some particular parametrization that's very nice. And what you want to take away from this is that, I have an array of these things. There's a set of 1D, there's many 1D wires. Each of them will have their own theta and their own phi. But I can rewrite it as an integral over d2r of all these things where the gradients pick some particular directions because each wire only disperses in one way or the other, right? So this is just some very complicated way of keeping that. And all the physics of whether the system becomes insulating or not comes from terms that are allowed by umklapp, by momentum-conserving processes that are only allowed at integer filling. Right? If I didn't have a lattice, I can't gap out the system because Liebschuld's lattice tells me the system will always be metallic. But if I have a lattice, then at certain fillings, I'm allowed to conserve momentum because I can backscatter a particle and absorb the momentum transfer into the reciprocal lattice. And so I'm going to focus on two specific umklapps that come from rewriting the interactions. One of them is a problem when a case when an electron scatters across the Fermi surface, an electron that picks up a 2kF backscattering. So, does everybody understand what I mean by 2kF backscattering? I take an electron one side of the Fermi surface and move it to the other. So plus kF to minus kF. That process turns out to correspond in this language to an operator that looks like cosine 2 phi. And this is a very relevant operator, but in the sense that if you think in the terms of renormalization group, its scaling dimension is very large, but it usually is not allowed because it's not a commensurate operator unless this 2kF times the filling is 6 times an integer. That's just some kind of geometry that you do to count the fillings. So that just says that there's some particular filling factors where this operator is enough. So if this becomes the most relevant operator, every chain on its own intrinsically is a strongly insulating state. So it's sort of a very, very strong insulating state on its own. Whereas there's also a case that remembers the system is in 3 dimensions. So this is actually a complicated beast. I'll call it O triangle. And this is actually a case where you survive the 2-dimensional sum because the electrons interact in such a way that there's backscattering on this wire, and this wire that together satisfy 6kF nu order 6z. So they transfer momenta at such a way that you get this complicated beast. So why do I have these two terms? It's because of the fact that at nu equals 3, this one is allowed. So if I put nu equals 3, 2kF nu equals 3 corresponds to this criterion, and this state is allowed. So every wire can be a Mott insulator on its own. That sort of intuitively makes sense. At nu equals 3, at the strong coupling limit, every wire has 1 electron per site in each flavor, and then that looks like a Heisenberg-like problem, and I can think of there being a strong Mott state there. at nu equals 1 or 2, you somehow have to rely on one of these operators to play a role. So you have to have this interchain processes that actually link the system in. So that's why this is comparatively a much weaker Mott state. So there's a nice sort of intuitive explanation from there. So why does this reverse at strong coupling? So at strong coupling, I should, instead of thinking about, yeah, it is valley, yeah. Yeah. Oh, that all comes from the, no, because there can't be any kinetic term between them because valley symmetry forbids that. The only terms that can come in are from the interactions, and those couplings are all cosines. Yeah, that's in there, right? Because the only way they interact when they cross is through a U, and that's termed like this, right? Because A, B, and C are the valleys, so this is a term that involves interactions between valleys. There's also two particle terms, but there's no way you can check from this where the valleys are in momentum space. There's no way for 2 wires to generate an operator. You need 3 of them.
Wouldn't there be a fourth?
What?
That
Momentum conservation rules it out if you do it carefully, just because of the way the valleys are set up. So I mean, there may be some details there. Okay, there might be another one, but it'll still be weaker than the intrachain ones. The basic principle still applies. I mean, this is a back of the envelope Bosenization. I haven't done the full calculation here yet. Yeah, are you happy with that, or you still him? I mean, you understand it can only come from the U's, right? It can't come because it can't come from anything else because of the conservation laws. And then you just have to do some momentum conservation arguments, but I think it doesn't quite work. It just comes from valley conservation as well. So, okay. Moving on, at strong coupling, you can instead think of the problem as being an insulating state and just asking, well, if I have a ferromagnet, let's imagine I'm in the alpha equals 1, the SU6 limit. Then I can just ask the number of directions that destabilize the insulator. So I just did some elementary combinatorics. 6 choose 3 is bigger than 6 choose 2 is bigger than 6 choose 1. So what that means is that at half filling, I have 3 of 6 possible states on each site fill. So the number of directions that magnet can fluctuate is much bigger than the number of directions that you can do at nu equals 2, and is much bigger than the number of directions at 1, which means since I'm doing finite temperature calculations, I'll actually melt this before I melt this, before I melt the other one. And actually, this is sort of well known in multi-orbital DMFT results, for instance. So what people have seen is that, there's some 6-orbital DMFT, and if it turns out that increasing the filling makes it easier to become insulating. So if you move away from, if you translate this to our language, it means that as you move away from half filling, it's easier to be insulating because the threshold to be a Mott state goes down. So there's sort of a nice intuition that basically boils down to the fact of number of fluctuation directions. This actually gives you a neat thing, which is like a Pomeranchuk type effect. So if I pick the case where the Mott threshold for filling 1 is smaller than the Mott threshold for filling 2, and I have an insulator, this should be filling 3, I can pick, a case where, I can pick this where, of course, 3 will be bigger than this. So what it means is that for this value of U, nu equals 1 is a Mott insulator, but nu equals 2 or 3 are not Mott insulators as T goes to 0. But it turns out that because they have quite a lot of entropy, if you increase T, you stabilize Mott insulators at those fillings, which is exactly a kind of Pomeranchuk effect, because you raise the temperature, and if it was in the Mott state, it could fluctuate. If it's if an itinerant ferromagnet doesn't have a kind of local moment entropy. And so this is sort of reminiscent of things that have been seen in beautiful experiments on TBG, for instance. And so it's just sketching that you can sort of see that. So what I want to take away from this is if I zoom in on these, you see that red is hotter and blue is colder. So notice that I go from cold to hot, and you see that the trend from blue to green going up is to see that I stabilize a sharper insulator here at a hotter temperature than down here. Of course, it goes away at the highest temperatures. Sort of a cute, actually seeing a Pomeranchuk effect just happen directly in a numerical experiment. And just as a teaser, we can also do this at any, because we can do anywhere on the doping axis is not special to integer filling. So if we work at fractional filling, we also see what looks like Wigner-Mott phases. So we can sort of see that. So going back to something that Hitesh said, we can sort of see Mott states also forming here at partial fillings as well. So I think I have about 5 or 6 more minutes. So let me just sketch the last set of numerical experiments we can do. So this, yeah. So this, I would say that, one thing we're trying to understand, so again, this is unpublished stuff, right? So this is only measuring the insulating physics. I've not talked about the spin physics at all. So we also have access to that. So what we're trying to do is, for instance, we want to connect it to that. We think we have it. It's not public, not, sort of ready for prime time yet. But what it is that you can actually ask about the typical dimer correlations and things like that. So we have data on all of that. I just chose not to show it. I can tell you more about it offline. It's just, being curated here. But yeah, we are trying to address to what extent can we match that strong coupling picture. It's not entirely clear. It's not easy to get that information directly. We're trying our best. So what this is at least saying is that at these integers, you form an insulating state. Sometimes you don't even form that. So in case where I don't form the insulating state, I shouldn't even believe any. That strong coupling picture starts with saying there's an insulating state, right? And so I can't even trust that unless I have an insulator. When in the cases when I can trust it, so nu equals 1 seems to be plausible at strong coupling, then I can sit and do that. Good question. So at half filling, I can do a different kind of Monte Carlo, which is maybe more familiar because it's been used a lot in TBG. This is what people call auxiliary field quantum Monte Carlo or determinantal quantum Monte Carlo. So the way you do this is you have an interacting fermion problem, and what you say is, well, I know I can trade an interacting fermion problem to a free fermion problem in some background field C, and this auxiliary field then has its own quantum dynamics. This is what we call a Hubbard-Svrtanovich transformation. It's a very standard thing. It's a fancy way of saying I complete the squares, right? Now, given this, I want to calculate e to the minus beta h for a problem that's this problem, which means I could be able to do that because I know how to solve any free fermion problem, because a free fermion problem, to calculate its partition function is just a determinant, so I can just do that. But then I need to actually do a sum. If I do a partition function of this problem, I then need to sum over the auxiliary field configuration, and I need to sample an object that looks like that. Now, e to the minus this is fine because that's a positive number, but a determinant famously does not have to be positive. But if you have an anti-unitary particle hole symmetry that's present, and it acts trivially on C, so the second feature is often ignored by people, you can have a symmetry that acts non-trivially on C, and that won't be any help to you. Then what that does is, what I mean to say is that if it acts trivially on C, then acting with the symmetry is really a property of this determinant for some fixed C, which allows you to fix its sign. It tells you that the determinant for each given C has a property that its sign is positive because the eigenvalues of that matrix come in complex conjugate pairs. And so that allows you to sample this because it's a positive number, and I can just do Monte Carlo. Let's just sample a positive probability distribution. And this is nice because it gives us access to imaginary time Green's functions, and by using Wick's theorem and sampling. And you can actually analytically continue to real time if you have enough high resolution data. There's actually packages developed by the group at Würzburg. Fakhr Assad's group has algorithms for lattice fermions that let you do this. You have to adapt it, but you can just run with this. And in our case, what we have to do is rewrite this interacting term as a sum of fermion square of fermion bilinears. You do that in some particular way. And what you find is that, the problem is this particle hole condition is that it's always present, but this trivial action on C, if you work on it carefully, only works if there's some particular criterion V over U. For alpha equals 1, this is V over U, V is less than, it's 3V is less than U, which, Hitesh, that was the line I drew earlier, was the U equals 3V line, where for alpha equals 1, this criterion fails. So this is when the determinant can no longer be applied, determinant prick can no longer be applied. That explains that dashed line. Okay. So I'll just flash quickly what the results are, because I think I have about a minute and a half left. So just to say there's not too many surprises here. So for the physically more relevant case where alpha is not equal to 1. So this is again the case where physically the particles have moved apart a little bit. The orbitals have moved apart a little bit. That's what we expect because there's no particular symmetry for this to be squeezed together. And in this picture, when T-perp is non-zero, you have two decoupled rectangular lattices in each valley, because remember, we couldn't have the first neighbor hopping. And so that gives me 6 copies of the usual SU2 Heisenberg antiferromagnet. In each of those Heisenberg antiferromagnets will have Néel order, because it's a bipartite lattice and 2D, very simple, you get Néel order. And it peaks at the zone corners, the rectangular Brillouin zone, which actually, if you kind of unpack it, turn out to be at the M points of the triangular lattice. So you get a sharp peak in susceptibility here. So you can actually look at those points, and what you see is a clear saturation of, for different values of this anisotropy. As I go down in temperature, I see a clear saturation of some proxy for the antiferromagnetic order. So it's a very clear signature here. But what's surprising is that if you go towards this artificial but interesting point of alpha close to 1, which again, you can get closer to that point depending on the material, what you see is, I think everybody can see from this, is a dramatic suppression for instance, at 9T, where alpha 0.75, 0.9 seem to saturate very well. I just kill the antiferromagnetic order down all the way. And at 12T, things seem to start saturating. So it seems like the antiferromagnetic order only saturates at much larger U over T. And even here, they seem to be finite size effects even at very low temperatures. So it sounds like the system stays metallic down to very low temperatures. And a way to think about that is to think about asking, there's a way, what this plot is showing is a proxy for whether the system has formed a good local moment, whether you're frozen out charge fluctuations and you really have something that's just spin fluctuation. So as a lower temperature, what you see is almost all curves follow this trajectory with a scale of order j, which is t squared over u. If alpha is not equal to 1, they seem to settle into this at this scale. You just jump into this phase. Whereas if alpha is equal to 1, they seem to follow a different trend. And what you can look at is to what extent are charges fluctuating between valleys as you go. And what you see is that those things get frozen out very quickly for all alphas except alpha equals 1. And one thing you can think about is in the anisotropic case, already you're doing perturbation theory about a point where you're a big scale for U6 breaking. So the system, so if you think about the problem there, this is broken and then J and J perp are like way down here. Whereas in the isotropic case, that is when alpha is 1, the U6 is only you sort of stay U6 all the way until the effects of the super exchange play its role. And you can sort of see that already just in what you can see is that the physics over here is the system eventually trying to find some broken symmetry state. But what you see here is that if I just take an atomic limits, it's just a single site, I do exact thermodynamics for a single spin and look at its fluctuations, charge fluctuations. What you see is that when alpha is not 1, you kind of settle down, you follow this trajectory very quickly. When alpha is 1, you sort of have this big U6 breaking. And so what you see is that this eventual turnover is really coming from just the t squared over u terms that have to break SU6 back down. So sort of a nice picture that you have this symmetric local moment over a wide temperature scale. And the very last thing I'll show, a bit over, is that if you analytically continue, you can ask, is there something special in this problem? So I can analytically continue to real time and extract A of k omega. And so what I'm doing is showing two axes. I'm becoming more isotropic. This is this SU6 versus SU2 cross SU2 cross SU2 problem versus more interactions. And what you see is when you're strongly interacting and symmetric, you sort of see that these very clear Mott gap features kind of go away, and you have very broad features down to very low temperature. So some scale is being pushed down very quickly, giving you a picture that, you have some story like this, where this is your interaction strength, this is your anisotropy. And what you see is that for the isotropic point, the metal seems to survive down to much stronger couplings and much lower temperatures. I'll skip the last thing, which is just an aside. If you actually want to figure out the ordered state, even in a single valley, it turns out to be a tricky calculation involving order by disorder or something like that because of the way the problem is. So let me just summarize and apologize for going a bit over time. These endpoint materials give you, I think, highly tunable examples of these mixed dimensional or sliding multi-orbital physics. And I told you how you get them in the first lecture. In the second lecture, what I've done is tell you there are two limiting cases. For T perp equals 0, we have unbiased numerical access to a doped Mott insulator without any local approximations, no DMFT in sight. You can just do it in a problem which kept the kinetic energy in the problem. Then I gave you a sketch of some of the rich physics. We are working on accessing Green's functions, which actually will allow you to perturbatively understand what happens as you add interwire couplings, so going towards 2 dimensions. And for half filling and T perp not equal to 0, so the 2D problem but at a specific filling, DQMC gives us some understanding of how this U6 symmetry might play a role in giving you some stronger metallic states. So let me say thank you for your attention and the questions.